some differential equations are what we call separable. They're written in such a way that the different variables can be separated out into factors, and you can separate to where you have just one variable on the left and the other variable on the right, along with their differentials. In this case, all you have to do is integrate both sides. I'd integrate this side with respect to y, this side with respect to x, and that gives me a solution that is maybe a little hard to solve for the variable y, but that's okay because the equation in the first place was given as an implicit. In other words, it's implied that y is a function of x, and sometimes the other way around, it'll be x as a function of y. But if they're separable, it doesn't really matter. So you can integrate both sides with respect to whatever the differential is with respect to, and that gives you a general solution, is what we call it. And as far as the constant of integration is concerned, we only need one of them because they can be combined. It's arbitrary, and so we just use one constant of integration. Let's look at this example. Notice that we are given a dy dx. It's implied that y is a function of x in this. So what I want to do, because dy is in the numerator here, I want to get this y over on the left-hand side and multiply away the dx. So we use algebra to get started. I divide both sides by y and multiply both sides by dx, and I get this equation. Now when I integrate both sides, the left-hand side is the derivative on top, function on the bottom, that's the perfect derivative of the ln of y. Integrating the right-hand side with respect to x, I get x squared, and don't forget my constant of integration. Notice that I put a little subscript of 1 here, because as I'm working the problem, when I come up with a different form of a constant, I'll just change my subscript, and in the end, whatever I end up with will just be c. So when I get this equation, I don't want the y to be inside the logarithm, so I'm going to rewrite this equation as an exponential. So the ln of y says that e to the what equals the function y. So when I rewrite as an exponential, the ln equals the exponent. So I end up with y equals e to the right-hand side. Now, if I'm adding powers, that means I'm multiplying e to this power times e to this power, right? But e to a constant is itself a constant. So I'm going to rewrite e to the c1 as plain old c being a multiplier of my function e to the x squared, okay? Notice that if I did not have that constant of integration, if I did not go through this mental process, if not writing it down, then I would not have that leading coefficient. It is absolutely, essentially important that you do not forget your constants of integration and that you manipulate them properly. So this example gives us a condition. Once we solve this differential equation, we're going to apply this condition and actually get our constant of integration. Now, first off, dy is in the numerator, so I need to somehow isolate a function of y and divide both sides by it and leave just a function of the x on the right and multiply by the dx. So you see in this right here, I can factor out an x. That leaves me a factor with just x and a factor with just y. So I want to divide both sides by 2 minus y and multiply both sides by dx. That gives me this separated differential equation. I'm going to integrate each side by itself and be very careful with your signs and your constants. So the left-hand side, the derivative of the bottom would be negative dy. So when I integrate this side, I have a negative ln of the denominator. Integrating the right-hand side, I get just a power rule integral of x plus some constant that I don't know. Now, I don't want to have a minus in front of everything, and I don't want to have this inside the logarithm. So the first thing I'm going to do is multiply both sides by -1. That gives me the positive logarithm is going to be a negative x squared over 2 and a negative c1, which I just chose to write as a different constant. C2 would be the opposite of C1. It's just a constant, so I don't care if it's positive or negative on the front here. Now from this point, I want to get my function outside of the logarithm. So I'm going to rewrite this equation as an exponential. That means that 2 minus y will equal e to this entire power. So we will have, just like in the previous problem, e to the constant times e to the negative x squared over 2. So we have e to the constant c2 we'll just call c3. Now to isolate that y, I'm going to have to subtract a 2 from both sides and then multiply both sides by a negative. Or I can just add y to both sides and subtract this thing from both sides, okay? That's going to give me positive y equals a positive 2 minus this thing right here, but minus a c3 just gives me a different constant. So I can write it this way, and then once I get this general solution with that arbitrary constant, I'm going to apply my constraint up here, my condition. This is usually called an initial condition because in the real world a lot of stuff is about time, and time doesn't go backwards. So an initial condition would be at time 0. That's for free there. So when I apply my condition, I'm going to set y equal to 9 and set x equal to 0. Well, e to the 0 power is just a 1. So 9 equals 2 plus a constant. That gives me a value of the constant, and it gives me my specific solution here. Now let's check and see if the solution that we got is actually a solution of the differential equation that we started with. So if y equals this, I can take the derivative of it and put it here, and then I can plug the whole entire function y right here and check to make make sure both sides equal the same thing. So when I take the derivative of my solution, I get this: 0 plus 7 times e to the power times the derivative of that power is minus 2x, which gets rid of minus 2x over 2, which gives me just a negative x with that 7 and the e to the power, which is negative, right? This is a negative power. Found my mistake. Good, good, good. So once I have this right here, I plug this into this part of the equation, the left-hand side. Then the right-hand side is going to be 2x minus x times my solution. Distribute that minus x through the parentheses. I get 2x. Now minus 2x, which goes away, minus a positive 7 e to the power gives me negative 7 e to the power, which exactly equals the left-hand side, and I know that I was correct. You will see a lot of this particular form of a separable differential equation, which will be the derivative equals some constant times a function. When we solve this equation, we're going to divide by y and multiply by x. This is so common. You'll see it over and over in your homework and in the real world. When we integrate the left-hand side, we get the logarithm. When we integrate right-hand side, which has a dx that I neglected to write, hold the phone. dx, then we're going to get the ln of y equals some number times x plus a constant. Rewrite this as an exponential. It gives me y equals e to this power, and e to this times e to this, that's just a constant, and I get this form of an answer. Another example, given this equation right here, the dy is in the numerator, so we multiply 3y squared and we multiply dx, and we get this separated differential equation. Integrate the left with respect to y, I get y cubed. Integrate the right with respect to x, and I'm going to get 4x squared and a constant. So it is perfectly fine to leave your answer in this form right here. Notice that in the question, the x's and y's were all mixed up, okay? You can, however, take the cube root of both sides and get this answer right here. Then you can check this by taking the derivative of the right-hand side and plugging it in right here, and then plugging that cube root squared right here. You'll see that some stuff cancels and you get the same answer on both sides of the equation. Next, let's look at this one right here. This problem right here, y to the negative, I multiply both sides by y squared, and I'm left with y squared dy and 7 dx on the right hand side, and we have a boundary condition or some sort of constraint to plug in at the end. Notice that I don't have the dx written right here. This is y prime. We understand, don't we, that y prime is dy over dx. So I multiply both sides by the dx, and I end up with this right here. Integrate this side with respect to y, integrate this side with respect to x. Don't forget your constant. Now, I want to get rid of the 3 in the denominator, so I multiply both sides by 3. Notice that c1 multiplied by 3 just gives me another constant, and that is perfect for finding your answer right here. I went a step further and took the cube root of both sides, but I could take my constraint and plug it in this form. So if I did that, I would have on the left-hand side 3 cubed equals 21x plus some constant. So 27, take away the 21, is going to give me 6, and that's what my constant equals. And then I can plug that constant back in and get y cubed equals 21x plus 6. This is just as valid an answer as this one is right here.